All right, so welcome everybody to Hoon Academy lesson one. So I hope you all enjoyed the first lesson. I hope that the homework was interesting. So today we are going to finally jump into what Urbit is and how to program in Hoon. Um, so far you may have heard a lot of talk about planets, moons, stars, and so on. What are these things exactly? So an Urbit ship is a running instance of Urbit with a unique network identity like sample palnet or Tamlet modnet. As a computer, an Urbit ship has state, which, you may recall in last lesson, ultimately reduces to data stored as zeros and ones, and operations, which are formal rules for transforming those zeros and ones into other zeros and ones. So your planet that you use on the network, and you probably got for the last homework, is what's called a live ship. So live network identities are finite and valuable. There are this many planets on the network, this many stars, and this many galaxies. So to be safe with these live identities, most people prefer to develop on what are called fake ships. So you can run Urbit instances on your local machine that are not connected to the wider network and that are replaceable. This is the main development method that we'll use in this class, but there are other options as well. So let's show you how to get started with that. So the first thing you'll do is you'll go to this link. Let me put it in the chat right now. Can everyone see that in the chat? Great. So using that link, you can download the Urbit binary. First, you'll want to go and find which architecture your computer is. So there's like different types of Mac, there's Linux, and so on. If you haven't done this before, I'd recommend you do it now and start the process so that you can follow along with the lecture. Um, so down the page, it tells you there's a command to install the binary, right? What you want to do is copy paste that into your terminal. And then, first you want to go to your terminal and navigate to where you'd like your Urbit directory to be. So here I'm in my home directory. I made this Urbit directory so I can see into it, but there you would just run that command and it'll make that Urbit directory for you. And now, so like I mentioned in the last course notes, Urbit is going to run on any Unix-based machine. And if you use Windows, we suggest either dual booting or using Windows Subsystem for Linux. Okay, so after you've done that, you want to navigate to your Urbit directory. Oops, oh, I'm already in there. And then you want to run the Urbit executable inside to boot an instance of a fake ship. We do that with this command. Does everyone see that command in the chat? So I've already booted mine, so I won't run this, but this is what I would do. And when you press enter, that's going to take a few minutes to boot that up. So it's going to run for a few minutes. So when a ship has already been created, you can simply run it with this command, /urbit zod. So in that case, zod is the one you've created. So let me boot my ship up. And just like that, now I'm in the Urbit environment. So now that we've booted Zod, we're introduced to something called the dojo. So the dojo is simply Urbit's command line environment, where you can use commands to access and manipulate your computer. So for example, we can go here and run ls, and then this is what we call sen. So this may look pretty similar to what you're used to seeing if you come from a Unix environment. So you know ls, probably, if you've done that before, right? So, and what this does is this lists all the files and folders in the home of my where I am. But what happens if so for the sake of teaching, I'm going to unmount this. So if I go to Urbit, this Urbit folder that I created, and then I go into the Zod folder, which I was just created, there's actually nothing here right now. This is what it'll look like when you have your Zod. There's going to be nothing there. It's kind of weird, right? Because when I was here, I could see all these what looks like files and folders, but there's nothing here. So what's going on? Now we're going to introduce an analogy called Earth and Mars. So Earth is your Unix computer, and Mars is where Urbit lives. So on Mars, Urbit organizes collections of code and data as desks. So each ship loads with just one desk by default, which is the send base desk. But if you want, you can create other desks too. And what we saw here is that desks are not synced with Earth by default. So if you want your desk to appear on Earth, you have to run the command var mount send base. And now, if we look over here, now this base folder appeared. If we click into it, here we can see all these files and folders, which we just saw in here. Okay. Were there any serious questions in chat? Michael Coppola says, my peer is replaying events 1 through 14. I'm pretty sure that's the normal message for when it's booting up. But if it takes a long time, if it takes more than like 5 minutes or so, then there might be an issue. And just let me know. I can help you after class. I have port on iOS. So I would not recommend trying to complete this course by running Urbit on your iPhone. That I would probably use a laptop or a desktop computer. For Windows, you should either dual boot. So I don't know why you'd be using port if you're using a MacBook Pro. For a MacBook Pro, that's a Unix-based system, so you can just do exactly what we're doing. For Windows, you should either dual boot Linux or use Windows subsystem for Linux. This will be in the notes. So the point is, you want a Unix-based machine. You can either like install that OS or simulate it using Windows subsystem for Linux. Windows is unfortunately no longer officially supported. Okay, so we just ran this command, mount base, and all these files appeared on Earth, on the Earth system. Okay, so how about the other way around? How do we get Earth to talk to Mars? So suppose you want to make some change to your Urbit, such as adding a file or editing a file. You would do this on Earth in here using your text editor, and then push the changes to Mars by running a commit command. So here's an example. A generator is a saved snippet of code that you can run from the dojo. So let's try to run a generator with this syntax. Let's say I have a generator called hello world. I'd run it like this. But actually, it's giving me an error because I haven't filled out that file yet. So what are we going to do? On Earth, let's open up a text editor. Oops. Let's go here. This is VS Codium. And let's open, oops. Let's go to Zod. Zod base gen. Let's open this hello world file. And there's nothing in there. So let's put some code in here. Let's put this code in our hello world file. And I'm going to paste this in the chat so you guys can follow along if you want. Let's just paste this into hello world.hoon, which we save in the gen folder of the base folder, and just save that. So now we should go to Mars over here and run var commit send base. And now it shows that there was a file that was changed. I'll also put that in the chat. And now if I run my hello world code, it returns the text hello world. So in future lessons, we're going to use this series of actions to store and run code that you're working on. If you want to close your ship at any time, you can just do bar exit like this. Or you can do Control D, does the same thing. We have a question, is there something Vim-like so I can edit files directly from the dojo? There are a few options to edit directly from the dojo, actually, or directly from the Urbit environment. I'm not going to recommend it because it's safer to use a fake ship like this, but it's possible, and I'll have notes. So there'll be extra notes in the notes on how you can do that if that's what you prefer. Okay, so as you're developing on a fake SOD, you'll quite often run into issues and maybe break it. So you'll want to like do something that can help you prevent against that, right? What you can do is you can make a backup, and it's very simple. So you just take your Zod folder and you make a copy of it. That's called Zod backup, right? So I'm gonna get rid of this for now, but you want to be on Earth and you just want to run this Unix command, which is copy the folder Zod into the folder Zod backup. And boom, you just made a backup. Whenever your Zod breaks and you need to restore, just rename this to Zod and then boot from there. That's it. All right, so any questions so far?
Yeah.
Cool.
How do I even start with all these commands? How would I know what to type?
Sorry?
You just type in, different commands and base and this and that. How someone like me never programmed before know what to type on the black screen like that?
Yeah, so we're in this class, we're telling you what to type. In the notes, it'll say, here's what you type to do this, here's what you type to do that. And the homework will have practice questions, which help you learn how to get more familiar with these commands. So this is part of the process.
Great, thank you.
Yep. Can you recap what's Earth and Mars? Earth is your normal computer. Mars is where Urbit lives. So they're not synced up by default, but you can use commands to make them to talk to each other and match up. Yep, that's a great answer, Lontus Rackriff. All right, any other questions? Cool. So the dojo is not just for poking around in your Urbit system and accessing files. You can also run Hoon code directly in your dojo. So something interesting to note is that the dojo will only let you input syntactically correct Hoon code. And if you try to type something invalid into there, it's going to stop you from doing so, and it's going to make a sound. So what do I mean by this? For example, in Hoon, numbers greater than 999 are represented with dots marking every 3 digits. So I can type 999 into here and press enter. Oops. Let me boot into my Zod. There we go. Now we're on Mars. 999, press enter, and it just returns 999, right? However, if I want to type the number 1,000, you guys hear that? It's not letting me type that third zero. However, if I want to type it correctly in Hoon, this is the right way to type 1,000. So this is like where the comma would go if you're used to the American decimal system, but it's just a dot. So now let me type 1,000. I also can't type a number like, if I try to press enter here, it's saying that's not a correctly formatted number because this dot is in the wrong place. The dots should go every 3 digits from right to left. So there's an example of a correctly formatted number. All right. So we are going to be using the dojo heavily throughout this course to work on our Hoon code. So it's good to get comfortable with using it. So I have a few useful tips and tricks for you to improve your dojo experience. So if I'm here, I just press up arrow. That goes through all the commands that I had previously typed in there. If I press down arrow, then it also goes down. And if I keep pressing down, then it goes back to the empty line. Okay, so if I press enter, and then the bracket is pointing this way, that means the last line was a correct piece of Hoon code. It finished computing, and now I can type another piece of Hoon code. I'm onto a new, fresh computation. If it's facing inwards like this, that means the last line was not a complete Hoon expression. It didn't finish computing. It's still waiting for some input to finish this last piece of Hoon. And then if you finished it and press enter, then it'll give you this angle again, this bracket. If you have an incomplete line of Hoon, you can also press delete or backspace, and that'll just like tell it to forget about what you had before. If you ever get stuck in like an infinite loop, for example, recall that in last lesson we showed you how like recursive functions can cause things to spin infinitely, right? So if that ever happens, you just do Control C, and that'll interrupt and break you out of there. If you have a long text line, then you can just do Control A to the beginning, Control E to the end. I think this is like Vim. And something interesting is if you type something and then you press tab, it tells you all the way you can complete it. So that's a useful tool. All right, any questions on that? I'm not trying to teach everything about the dojo right now, but those are just a few tips and tricks. They'll be in the notes. All right. So what exactly is an Urbit computer? So we discussed last week that information is data plus interpretation. So on one level, your Urbit is a very long sequence of ones and zeros. And if we go up to the highest level of interpretation, it's a computer that lets you use apps, talk to other computers, and so on, right? But in between those, there's different levels that we could understand the computer on, and that's the level that you're going to be working at if you're writing a programming language. So if we go up one level of interpretation from the binary 0-1 code, we can say your Urbit is a big binary tree of natural numbers, which are non-negative whole numbers like 0, 1, 2, 3, 4, 5, 6, and so on. This binary tree structure is at the heart of the Urbit system, so it's important to understand it well. So in Urbit, what's called an atom is a single non-negative whole number. So like this, these are all atoms, right? 0, 5, 1.566, so on. A noun is defined recursively, meaning a noun uses its own definition in its definition. It's not that complicated. So a noun is either an atom, so like just the number 5, right? Or it's a cell of two nouns. So in particular, it can be a cell of two atoms, like this, 4 and 3. It can be a cell of two atoms in an atom. It can be a cell of two cells, each of which are cells of atoms, and so on and so forth, right? You can make increasingly more complicated binary trees like this, right? Wait, so I just used the word trees, but these are like cells. There's like brackets of numbers, right? So what's the connection between those two things? Look at this graphic here. That shows you the correspondence. So cells of cells, binary trees. So number 5 is just 5. 5 and 2 is a tree that's split like this. 5, the cell of 5 and the cell of 927, the tree like this. And notice how in each of these steps, we're taking a number, like here the 2 becomes a 927. We're taking a number and splitting it into a cell of 2 numbers. And in the tree, you'll see that one node in the tree is splitting into 2 branches, each with a node, right? So here we split the 9 into 0, 1, 9 replaced with 0, 1, 5 replaced with 8, 9. So does that make sense to everyone? It's an important concept.
Question, Jack.
Sure.
Fourth line, 50127. How do you know that the old one is attached to the left-hand side of 27?
Oh, so because if you look here, this 9 and 27 are in a cell together, right? And what we did was we just replaced this 9, the single thing, with a cell of 2 things. So whatever's there is always going to be attached to this 27 because they're in this bracket together, right? So we replace this 9 with a 0, 1, and that means this, it's still attached. Does that make sense? Does that mean something is invalid? So I think we'll answer this question later. So yeah, we'll get there. So if we're storing data in our Urbit using these binary tree structures, we need to be able to access different parts of the tree, right? So how do we do that? We can number the nodes of the tree as follows. So you can say the whole tree is 1, then this left subtree is 2, this right subtree is 3, the left subtree of the left subtree is 4, the right subtree of the left subtree is 5, and so on and so forth. If this is a complete tree, then you just keep numbering it like this. So that's, and you could imagine how 16, 17, 18 would be below here, right? If you want to grab the whole tree, you're going to use the address 1. And if you want to grab the left subtree, use the address 2. Right subtree, you use the address 3. Let's look at an example of this. So here we have a noun. It's 8, 9, 10, 11, 12, 13, 14, 15. And it's this cell structure corresponds to this tree, like this, right? So if we grab address 1, we're going to grab the whole thing. If we grab address 2, we're going to grab the subtree 8, 9, 10, 11. And that's going to correspond to this part of the cells, right? If we grab address 5, 1, 2, 3, 4, 5, that's going to give you this subtree, and it's going to give you 10, 11. And if you grab address 10, that's just going to give you the number 10. So to see this correspondence better, we can actually represent the tree like this, right? So this is the same thing, but we just wrote what you're going to get if you grab that address in each node, right? So this bottom layer is the same, because if you grab any of these addresses, you're going to get just that. But this is saying if you grab here, you get the whole thing. If you grab here, you get the left subtree. If you grab here, you get the right subtree, and so on, right? So let's use this same tree that we just examined and try these addressing operations in the dojo. So first, we need a way to store a piece of data in the dojo's memory using a name so we can access it later. In Hoon, this is called pinning a face. And what we're about to write here, it's not technically Hoon code, but it's like a dojo specific shortcut. And this distinction will be important later, like in lesson 2, but don't worry about it too much. But basically, I just use this syntax, equals a 1. And if I call a, I get 1, right? supposed to be 2. I get 2, right? Type that in the chat. So now what we're going to do is we're going to say equals tree, this whole thing, right? Now we're going to store this data structure under the name tree. And now we can grab subtrees of the tree with the following syntax. So let's say I want the +5 address. 1, 2, 3, 4, 5. That should give me 10, 11, right? So I do +5 dot tree. It gives me 10, 11. Do +10 dot tree, and I get the number 10. So this dot right here in between two expressions means we are searching for the address +10 within the thing called tree. And we can even use this dot repeatedly like so. So this is saying in the subtree of the tree at address 5, 1, 2, 3, 4, 5, let's get the 2 address within that. So what's the 2 address within here? 1, 2. That should be the number 10, right? So boom, get the number 10. Why is the plus here? It's just convention. Is there a minus? No, there's no corresponding minus for this. It's just like a convention that indicates you're doing addressing. So here, let me put all these in the chat. All right, any questions on that so far? Is the dot, no, the dot is legal Hoon. The only thing is that wasn't legal Hoon is this like equals tree thing. This is dojo specific. Equals a, so on. But this dot is legal Hoon. Yep. Okay, so if there's no more questions, we'll be moving on. So when we're using computers, we might not always want to express things as pairs, right? For example, like we might want to represent an object that contains 3 things or 4 things or 5 things or so on. How do we express this? So in Hoon, we do it in the following way with the same tree structure, cell structure underneath, but just branching out rightwards like this. If you type a structure like this with this rightwards branching structure, the dojo is going to pretty print it. So these are the same, but this 1, 2, 3 is just going to print it as 1, 2, 3 without any other brackets. This can be a little deceiving at first, but it's important to know that these correspond to the exact same data structure underneath. It's just printed in a way that's a little nicer to look at. And we can test this in the dojo. So let me put this 1, 2, 3, and you get back 1, 2, 3 without these inner brackets, and 1, 2, 3, 4, and so on, right? So does that make sense, everyone? The rightwards branching is like repeatedly expanding this innermost right thing. So here, this 3, 4, this 4 expands to 4, 5, so on. Doesn't that obscure the way the branches are grouped? Yes, it obscures it. Like there's no information lost, but it does because you're not going to see a cell with 3 things. If you ever see a cell with 3 or more things, then you know it's hiding some brackets. But it does maybe like from a computational, like if you're like really autistic about it, maybe this is a little harder to read than this. Like it kind of obscures the underlying structure a little bit. All right. So is it non-ambiguous? Yes, it is. This is non-ambiguous. There's no information lost in this mapping. I see you're pasting into dojos at Control V. Yes, Command V for Mac, but yes, you can just copy paste into there. All right. So before we were using addresses to navigate within this tree, right? In the real world, that's kind of like saying, go to 200 Main Street in Springfield, Illinois, right? So we have this, like maybe Illinois is like take the left branch, Springfield is like take the right branch. Like you get an increasingly precise instruction within that, right? However, in the real world, you can also navigate with instructions like go right for 1 block and then go left for 3 blocks and then go right and so on and so forth, right? So in Urbit, when you're navigating a tree, this is called LARC notation. So LARC notation uses the 4 characters, which are minus, plus, and this left bracket and right bracket. You always begin with a minus or plus, and then you use a left bracket or a right bracket, and then you use a minus or plus, and then you just keep alternating those. But minus means go left, plus means go right. So if we return to our previous tree example, so this is still saved in the dojo. But we can just, here's the instructions for it if you need to use it. And if we do minus.tree, it's going to give us the left branch, plus.tree, the right branch. And you can keep navigating like that. So back to our analogy of navigating in the real world, sometimes addresses are so notable that you don't need specific directions like this, right? For example, if I said, go to the Eiffel Tower or go to the White House, that clearly conveys where you should be going. In Urbit, we can assign what are called faces to parts of our tree. So let's change our tree a little bit. This is the same tree. This is the same structure as before. Now we've attached these faces to parts of the data, right? So A is 10, B is 11, C is this cell, and D is 12 within that cell, right? So now if I do A.tree, I get that 10. You do B.tree, I get that 11. C.tree, get that cell of 12 and 13. And I can even do D.C.tree. So that says, look for D within C within the tree. That gives me 12, right? You can even use duplicate faces. So when you call a face like A, Hoon is going to perform a depth first search and return the first match that it finds. If you're not familiar with what a depth first search is, basically you're gonna always take the left branch, go all the way to the bottom until you can't go anymore. Then you're gonna back up as little as possible, take the right branch, and then if you can't go anymore, back up until you can take a right branch, and then just keep going left as far as you can, and then back up like just 1 step. So there's also resources online, but basically it's going to search like that for the first match. Let's try this example. So here we have a data structure in which there are several things called B. If you do B.T, it's going to return this first match that it finds, which is 1, right? But we can actually search for the next match as well. With this following notation, this character is called a ket. This just says skip the first match and find the next one. Boom, we got the 2. We can do ket, we get the 3. And we can do ket, get the 4. All right, any questions on that? Chaser says, why not only use plus and minus for LARC notation? That's a good question. I would guess that this was implemented for legibility reasons. like maybe a bunch of minuses in a row is hard to read, you know. But yeah, I wasn't involved in the design, so. All right. So if there's no questions, I'll move on. So we have just given a brief overview of the way that data is stored in your Urbit. However, we said nothing about how the computer actually computes things. So let's recall the functions on a binary tree that we introduced in last lesson. So recall that any functional procedure consists of two parts, the data input and the computational instructions on what to do with the data. So in this image, can you identify which part is the data input and which part is the instructions? I mean, I've labeled one of the parts, but surely someone knows the answer, right? Yep, 1782 is the input, and the instructions are to increment and the right subtree. Yep. So we could also rewrote it like this. Let's just cleanly split this up. The data is this tree, 1782, and the computation is to take the right subtree of the input and then perform increment on that, right? And here are the steps you would take to reduce this pair of data and computation to a result. So this is what it says. Now we're going to reduce right subtree. So we're going to take the right subtree of this, which is 2. That reduces to increment 2. Then we reduce the increment, and we just get 3, right? And like, here's another example, just to get comfortable with this idea. So here we have data same. Computation is increment left subtree of the input. So we reduce the first left subtree to get increment left subtree of 17.8. Then we reduce the second left subtree to get increment 17. Then we reduce the increment to get 18. All right. So let me just rename things. I'm actually going to call this data the subject. I'm going to call the computation the formula. We're getting close to something that resembles NOC, which is the formal system, the machine language that underlies Urbit. So a NOC computation consists of two parts. The subject is the data input, and the formula is the computational instructions. However, unlike this pseudocode we have here, both the subject and the formula are binary trees of whole numbers, positive whole numbers, right? So, but just like here, the formula is going to contain clear instructions on how to transform the subject and return a result. And it's just like this, except this, instead of English, it's encoded in numbers. All right. So to understand this, let's look at some examples. Knock 0 is a code that says, take the number immediately after the 0 and return what's at that address in the subject. So what's our subject here? This is the same tree that we were looking at before. 8, 9, 10, 11, 12, 13, 14, 15, right? It's the same tree. And the formula 02 says to take what's at the 2 address of this and return it. So the 2 address, one address is a whole tree, so the 2 address is the left subtree. And we're going to return 8, 9, 10, 11. Right? And we could have just interpreted this in plain English, right? We could just grab subtree at address 2. And in Knock, you can chain together instructions as well. So here we're going to return to the plain English. We're saying, here's a subject, right? Increment the result of taking the subtree of this at address 2. That's what we want to do. So these are the instructions. Reduce this instruction, which reduces the increment 50, right? Because 50 is at address 2 of this. Then increment 50, 51. All right. So here's the exact same thing in knock. So knock 4 is a code that says compute the formula that comes after on the subject, and then increment whatever came out of that. So what's the formula that comes after? Well, here's 0, 2, right? We just learned what 0 does. It says go to the subject and grab what's at the 2 subtree of it. So here's our subject formula pair. It means increment the result of computing 58902. We're going to grab the 2 address, which is just the number 50, and then we're going to reduce this increment, and we're going to get 51. Does that make sense to everyone? If you have any questions, now's the time. Yeah, the 0 says look at the whole subject and then use the number immediately after it to go to the address. So if this was like 10, right? There's no address 10 in the subtree. So if this said 0, 10, your formula would crash, right? Just like in our exercise, we had a crash if you tried to access a subtree that didn't exist. If you're following on the knock spec, knock 0 is start A, correct? I'm not 100% sure what you're referring to, but probably. I'd have to look at the spec again. Yeah, I can follow up on this after the class since I don't want to be like staring at that and take a bunch of time. But yeah, good on you for following that. That's higher level, or that's more detailed than I was planning to go into. How do we type this in the dojo? Good question. We're gonna get there. Actually, we'll get there. Yes, you can type knock in the dojo. Yes. So, another knock instruction. So, knock 3 says compute the formula that comes after the 3 on the subject, and then return 0 if that result is a cell and 1 if it's an atom. So how do we reduce this? Well, this says compute 0, 2 on the subject. 0, 2 means get the thing at address 2, which is 50. And then we're saying this is atom, not a cell, right? So we're going to return 1. Knock 5, a 5 should be followed by 2 formulas. And knock 5 says compute both of those formulas on the subject, return 0 if those 2 results are equal, and 1 if they're not equal. So here the 5 is followed by 0, 2, 0, 6. 0, 2 means go here, get the thing at the 2 address. 0, 6 means go here and get the thing at the 6 address, right? So we're going to compute both of those. The thing at the 2 address is 50. The thing at the 6 address is going to be 8. 50 is not equal to 8, so this reduces to a 1. So yeah, 0 is true. That's right. And we'll get into that in a little bit. So the point of this section is not to fully understand knock. However, we do want to get the flavor of it. Knock is a simple mechanical formal system based on binary trees that underlies all of Urbit. The Hoon language compiles to knock and is close to it structurally. So by getting a feel for knock, we're going to get a feel for why Urbit and Hoon are the way they are. All right. So let's begin our dive into the Hoon language. So you may have heard of runes, right? Runes are combinations of 2 symbolic characters, and they're Hoon's way of specifying different operations. The simplest possible rune we can learn is the rune to make a cell. And this rune is called Cohort. So if I do Cohort 1, 2, that is going to make a cell with the numbers 1 and 2. And we don't have to give just atoms as inputs. We can give cells as inputs too. So here we made a cell of the cell 1, 2, and the number 3. So something very important to note about Hoon's syntax, spacing is important. So Hoon differentiates between an ace, which is exactly one space, and a gap, which is 2 or more spaces. So if I try to type this previous code, I want to do colhep 1, 2, but if I just make one space there, it's not even going to let me type that one. See, it's making a sound. But I can make a bunch of spaces like this, and it works. I can even press enter. Oops. I can even press enter in between, and that also works. So 2 or more spaces or enter is syntactically the same. One space is different. Okay, so we mentioned that this rune is called colhep. Hoon has a system by which every symbol is mapped to a monosyllable name. So this thing is called col and this thing is called hep. Runes are organized into families based on their first symbol. So every rune that starts with a col is used for making cells, except for col. That's right. Col is an exception. But every other col something is about making a cell. So you don't have to learn all the names right now, but we will, as we start to use these runes, we're going to introduce you to the names and you'll learn them over time as you gain more facility. All right, so let's go back to our humble colhep rune. So here's something interesting. Col is short for colon, yes, pretty much. So here's something interesting. The colhep rune takes 2 arguments, right? But what's going on here? What's the second argument of this colhep? What's the second argument? It's not a number or a cell, but it's actually another rune, which itself has 2 arguments, right? Is that okay? Turns out, yes, that's perfectly fine. So colhep is a rune with 2 children. Each of these things should be nouns, like 1 and 2, or cells or whatever. But they can also be complete Hoon expressions that reduce to nouns. So in this case, colhep 2, 3 was a Hoon expression that reduced to a cell of 2 and 3. And then that was a valid second child for this outer colhep. So just like this, right? This is what's going on. This was in this child. We can even parse this as like a syntactic tree. So this has 2 children. This one is the first child, and its second child is this whole expression, which itself has 2 children. So let's look at a similar Hoon expression. Stefan says, is the differentiation between 1 and 2 plus spaces peculiar to Dojo, or does Hoon source code look like that too? That's a Hoon convention. So, and yes, it is readable. You get used to identifying which things are 1 space and 2 space. They have like different contexts in which they're used. So, yeah. There's never a situation in which like 2 symbols could be separated by 1 or 2 spaces and they'll mean different things. Like that doesn't occur. Okay, so let's look at this piece of Hoon code. So maybe this looks kind of confusing, right? Is this rune like a child of this rune? Does this have 3 children? But actually it parses in the following way. So this is expecting 2 children. This is expecting 2 children. This grabs the 1 and 2, and then boom, this rune is finished. That's its own complete tree. And then that whole thing becomes the first child for this rune. and the 3 becomes the second child. So in general, Hoon is going to be parsed from innermost to outermost, and you'll go into the sub expression. So here's another expression, right? Here you'll say, I'll go into here. This expects 2 children. I'll go into here. This expects 2 children, 1 and 2. Okay, you're done. We'll compute you. We'll turn you into this cell. Keep reading. We'll see this. You expect 2 children here. Grabs us 3 and 4. Computes you. Turns you into this. Okay, now you have 2 nouns for this. And now you can reduce this into the result. So here's an incomplete Hoon expression. Can you guys tell me whether it's the inner Kohlhep or the outer Kohlhep, which is still missing a child, which is making this incomplete? Yep, outer. Very good. Yep. How about this one? Is it inner or outer that's missing? Yep. Very good. Very good. Nice. Good comprehension, guys. All right. So that's a very simple room, right? Are there any questions so far? All right, so let's learn some more things we can do in Hoon beyond just making cells. Yes, every Kohlhep expects 2 children. That's correct. And every rune is going to expect a certain amount of children, like that's just built into its definition. The last example, yes. So this is gonna parse like this. And remember, there's an invisible bracket around 2 and 3. All right. So just like knock, every Hoon computation actually consists of a pair of subject and formula, which, if you'll recall, is data and computation. So the next rune we're going to learn is called Tisgar. This rune sets a pair of subject and formula and computes the formula against the subject. So let's try some examples. Michael, no, those are 2 different structures. All right, so here's the tree we had before. We're going to say, set this as a subject, and this dot refers to the whole subject. So what this piece of code means is set this tree as a subject, and then return the whole subject. So boom, we just got it back, right? We can also do addressing like we were doing before. So here we're saying, set this tree as a subject, and then return the +2 address of the subject. Set the tree as a subject and return the +4 address. Set it as a subject and return the +8 address. So this, what we learned here, is basically the equivalent of the knock opcode 0 that we learned before. There's another rune called Tisgal, which is literally just the same, except the arguments reversed. People use this to make code prettier, to reverse the arguments, but here's an example. Oh, oops. There we go. So it's just the same, arguments reversed. So the next rune we're going to learn is very simple. It's called dotless. It takes a single child, which should reduce to an atom, and returns the atom incremented by 1. So this code, which doesn't use the rune yet, says set the number 5 as a subject and return it, right? Returns 5. This code says set the number 5 as a subject and increment the subject. Dot less means increment whatever is here. This dot refers to the subject, so we're going to return 6. And this says, let's set the cell 3132 as a subject and increment what's in the +3 address of the subject. +3 address should be this 12332. We're going to get 33. And this is basically the equivalent of the not code 4 that we just learned. However, if I want to add the number 1 to the number 5, do I need to do all this, right? I can actually just do dot less 5 and get 6. But earlier I said every Hoon expression has a subject and a formula. And it looks like this is just a formula. So what's going on there? And it turns out every piece of Hoon that you type into the dojo is implicitly wrapped with a tizgar. It's invisible. This is like an invisible piece of code that's wrapping the code that you put in here. And the first argument to that is going to be what's called the default dojo subject. This default subject gives you access to a lot of things, such as standard definitions and libraries. It's a very big thing. And so when I just type this dot less 5, it's like I put that dot less 5 in here, and then I evaluated the whole thing. So this is always there when you're typing code in the dojo, even if it doesn't look like it's there. Does that make sense to everyone? So there's always a subject for every Hoon computation. Yes, Darset Labrum, that's correct. All right. So moving on, there's one more rune. This is called dot what. This corresponds to the knock 3 that we learned earlier. So we're gonna reduce this Hoon. If it's a cell, you return 0, and if it's 1, or if it's an atom, you return a 1. Will Hoon ignore tizgar if you supply it anyways? I'm not sure what you mean by ignore. Like, if you, maybe you could clarify that question. Or you can ask afterwards. So this dot what corresponds to the knock 3 we learned. So let's see an example, right? This code says, let's set 589 as a subject. And what's at the +2 address? Return 0 if it's a cell and 1 if it's an atom. Well, the +2 address is the number 50. So we're going to get this send.n. No. And what if we do the +3 address? That returns as 89. We're going to get this yes. Let's learn one more rune that corresponds to knock. This dot tiz corresponds to our knock 5 that we learned. It takes 2 children, runs both of those against the subject, and returns 0 if they're equal and 1 if they're not equal. So, for example, here we're saying set 589 as a subject, and we're going to ask, is the +2 address equal to the +6 address? No, it's not equal. But we can also run this without this tizgar wrapping it. Is 1 equal to 1? Yes, it is. Is the cell 1, 2 equal to the cell 1, 2? Yes, it is. Now, we said earlier that these runes return 0 or 1, but it actually looks like they're returning the send.n and send.y. So what's up with that? It turns out send.y is actually just the number 0 underneath, and send.n is a number 1 underneath. This is what's called in Hoon a Lubian, which is Urbit's version of a binary yes or no. And the name Lubian is because it's reversed from what we usually expect for a Boolean. So yes, 0 means true, 0 means yes, and 1 means no or false. So we can even test this with this dot tiz. So dot tiz send.y 0. Yes. Dot tiz send.y 1. No. Dot tiz send.n 1. Yes. that make sense, everyone? All right. So our final section of the lesson. So far, we've only been working with natural numbers. Why is zero true? You have to ask the very famous blogger why that is. But actually, it makes sense to me because it's like kind of like truth being like the default state and one being like the negation of the default state, if that makes sense. There's actually a few other languages in which zero is true. I think there's languages in which returning zero means everything worked, there's no issue. And then returning one or any other number is like some sort of error code. So yeah. All right. So far we're just working with natural numbers, but for practical computing purposes, we're going to need more data types than that, right? So we're going to need negative numbers, floating point or decimal numbers, text strings, and all these things for having a regular computer, right? So in Knock, every atom is really just a natural number. So it's really just 0, 1, 2, 3, 4, and so on for Knock, right? However, Hoon has more options for representing data. And Hoon's type system is like a metadata layer over Knock, which tells you how to interpret these underlying numbers in different ways. So, for example, we just saw that send.y is actually equal to the number 0 underneath, and send.n is equal to the number 1, right? Urbit's famous sig symbol is actually just 0 underneath. It means 0. And so is the galaxy Zod. That's just a way to interpret the number 0. So what's called an aura is a way to parse an underlying natural number into a different representation. So the most simple and basic aura is just what we call pat, like the at sign. And you use this syntax. So I can just cast the number 100 to the aura pat, and it just returns a number 100. If I cast the galaxy Zod to that, then I get the number 0. And cast send.y, I get 0. So this is revealing what these all are underneath. We can represent fractional numbers with the aura pat rs. So for example, I have this big number. I'm going to cast it to a pat rs, and what do I get? I get 3.1415. So fractional numbers in Urbit always start with this dot to differentiate them from whole numbers. I'll put that in the chat as well. So we also have binary and hexadecimal numbers. So binary numbers are just whole numbers represented in base 2 instead of base 10. Hexadecimal is whole numbers represented in base 16 rather than base 10. So if you haven't seen them before, they're not too different from like our regular numbers. But we can cast any number to a binary number, like so. We can cast it to a hexadecimal number, like so. And we can represent the backticks are like Urbit's way of saying cast this atom to something. So we'll learn more about it later, but it just means cast something. That's as far as we can go for now. So the text aura is pat t. We can convert this big number into a pat t and get the text hello, right? So this just telling us the text hello is this number underneath. And we can convert things to ship names as well, which are represented by pat p. Here, if we convert this number to pat p, we get sample telnet. So, and we don't have to start with a number. We can also go directly into between different auras. So, for example, if I cast this, which is what looks like a PAT-P, this looks like a ship name, right? If I cast this to a text, I actually get the text hello. So that's saying the number underneath here is the same number that when cast to a PAT-T represents hello. That makes sense, everyone? All right, good. So there's a lot more auras than we can cover here. But you'll learn more about some of these as we go on in the course. Why would hello have its own ship? Hello does not have its own ship, but what did I do here? So I'm going to take the text hello, and I'm gonna say, what's the number under here? What's the number underneath this text string? And it's this big number. And then I'm going to take that number, and I'm going to say, I want to interpret this number as a PAT-P, and then I get this DASPEL BigReg FAMTL. And then I can cast that back to a text, and I get hello. Does that make sense, Franklin? Yep. All right. So, end the course for today. Went a little bit over, so thank you for your patience. But in short, we've learned a lot of things. We learned how to set up your fake ship for development. We learned how to sync files between Earth and Mars. We studied how to address and manipulate binary trees and the fundamentals of Nock, which is Urbit's machine code. We began our study of Hoon with some straightforward runes and learned how Hoon corresponds to Nock. And finally, we learned about auras, which is Hoon's type system for single numbers. And if you made it here, congratulations on starting to get a handle on Hoon. This is a lot, but yeah, I hope you enjoyed it, and I hope you're learning. So yeah, thank you for being here. Sorry I went a little over, and I will stop the recording now.